Now, a lot of work's been done, and this is where I spend a lot of time myself, extending online simple scheduling algorithms based on priority like EDF and deadline monotonic to a multiprocessor environment. First using partition scheduling and then using global scheduling. Partition scheduling is where we apply the algorithm locally on each processor and statically assign tasks to processors. The beauty of that is that it has some of the advantage of static scheduling. We have fewer combinations of interleavings and concurrent events, and therefore more predictability, more repeatability, fewer things that can go wrong, easier to model. And we can use, for mutual exclusion, as long as tasks are sharing data only on the same processor, we can use lightweight local locking techniques. Global scheduling has some advantages, though. It idles the processor less, gives you better average throughput. You can prove that by queuing theory, that definitely get better average throughput by having a single queue for multiple processors. And there are a lot of results for scheduling. For partition scheduling, optimal scheduling is still NP hard, but just like static scheduling, we can use non-optimal algorithms with heuristics, and we can get good results. And we can show that we can get at least 50% utilization before failure, and on the average, a lot more than that. This is a 50% bound. If we have 3 tasks and 2 processors, and each of them takes 50% plus epsilon of the CPU, then we can only fit 2 of them on with partition scheduling. For global scheduling, there is an old result that was often cited as why global scheduling is bad. And it says take 2 tiny tasks and 1 huge task and set them up like this so the tiny tasks have deadlines that allow them plenty of slack, and the huge task doesn't have much slack. And what will happen is that if we used earliest deadline first, or rate monotonic, or deadline monotonic, these guys with the shorter deadlines will get in front because they're greedy and they have shorter deadlines, and they'll push this other guy with a tight deadline that's longer out, and he'll miss his deadline. That's bad. Okay. But this is the whole story. There's a lot more to it than just this is bad. This is also how you solve the problem, too. You recognize that these big tasks are bad, and they shouldn't be treated that way. They're special cases. If you recognize that as long as the tasks are all short, this won't happen, and if you recognize as long as you take the big tasks and handle them a different way, things aren't nearly so bad. It works pretty well. And you can capture some of this intuition by one of the basic schedulability tests, which we call a density bound. It uses a density function I mentioned before. This is the density of the ith task. This is the maximum over all tasks of the densities. If I have m processors and n tasks, so I take the total density of the task set, it's less than the number of processors minus that minus 1 times the maximum density. It's schedulable. And you notice if the maximum density is small, this gets better and better and better. If the maximum density is large, this converges to 1. If the maximum density, task density is 1, this formula collapses down to 1. But the smaller and smaller the maximum density gets, the smaller and smaller our tasks, the better and better the utilization, or the density bound we can get. Intuitively, it's derived like this. I mean, if you have m processors, you take the same example we just had, generalize it to m processors, and I can force a task to miss its deadline by only keeping all my processors busy for this much time. But how much is that? And how much is left? That means I'm going to have an idle time that's m minus 1 times the length of the whole interval here times the maximum density. And so the total amount of work that gets done here is m times delta, that's the length of interval, minus m minus 1 times delta max, which is what we've got here if we divided the whole thing by delta to get the density. So the argument is a lot more complicated than that, but that's basically why it's true. And that's a nice, simple result. It's not as precise as some of the other tests that have been developed, but I like it because it's intuitive and it helps you understand why this example that shows the worst case is in fact, not necessarily so bad if you have a lot of small tasks, and it's really the crux of it is having large tasks. And so one of the solutions to this that works pretty well is hybrid scheduling. You take those big tasks and you assign them top priority. Say they're special cases. And then everything else gets scheduled by global scheduling. It turns out with that we can get a utilization bound of m+1/2, which is as good as you can get with partition scheduling in the worst case. The intuition again here is though that long jobs are actually good if we start them early. The fundamental goal of multiprocessor scheduling is to keep all the processors busy. That's the way we get maximum throughput. That's the way we reduce the backlog. And by having a small backlog means we get good response time when tasks come in. Now you can get down to little details like what is the backlog in terms of is it higher deadline tasks we're interested or higher priority tasks. But it's always the case that there's a backlog of tasks that are ahead of whatever task you're concerned about. And the backlog is what makes it late. And if I can get the backlog down, then I get good response time. So long jobs are good because they keep the processor busy for a long time. And that's generally a good thing to get a lot of throughput, as long as we get them started early enough that we can interleave them with other things. And we'll be happy when we have them around to keep processors busy. So we basically want to start our long jobs early and have an opportunity to execute them over a long period of time. Now, an extreme of that is, and this is an optimal scheduling algorithm, is the fluid scheduling algorithm. A family of algorithms, they're called p-fair in general. There's a bunch of variations on this, but the basic idea is we slice time sufficiently small that it approximates the behavior of a fluid. So instead of having two processors, we have processors of variable fractions of size, speed. And if we have these two tasks here and this long task here, we can give the two tasks each a fraction of whatever processors are available. It's sufficient to get them done by their deadline, by time slicing them. Now, it doesn't look like this. It looks like a whole lot of little vertical slices interleaved. But the net effect is as if we had fractional processors. And we get started on J3 early and give it a little bit of time. And when the other guys get done, we give it a lot of time. But we can't give it more than 1 unit of time. That's because it's only one job. And that's why it's really important to keep all of our processors busy, because one job alone can never take advantage of more than one processor. We want to have a lot of jobs around so we can keep all the processors busy. And in fact, you notice it doesn't finish until the very last moment, because it is keeping all the processors busy. But yet it's optimal. You can get up to 100% utilization, which is the best you can do without going over your deadlines. Now, there's a lot of other algorithms. One of my favorite algorithms is earliest deadline zero laxity, and I'm not going to tell you much about it except what it is. And that's where we take earliest deadline up until the point where we have no slack time left, where if we don't start executing right away, we're going to miss the deadline. And we immediately bump the priority of the job up to the maximum. And that gives you much nicer performance than ED and earliest deadline. There are tests for that. And there's a lot of other variety of tests. And at this conference, you're going to hear some other kinds of methods like task splitting, for example. I saw there were 2 papers in the proceeding on that. So this is a really hot area, lots of new ideas coming up for trying to get better utilization out of the processors. There are extensions, which I don't have time to go into, but I'll mention briefly. Aperiodic servers. If you've heard about sporadic server, for example, you can make it, if you make it work on a multiprocessor, you can run your sporadic server if you can run a sporadic task. And the schedulability analysis for the sporadic server is the same as the schedulability analysis for the sporadic task on that processor. Locking protocols. You've heard about priority ceiling and so forth. Oh, I should mention, sporadic servers, one concern I have personally is that on multiprocessors it's tempting to have budgets not by individual servers, but by groups of servers if you had multiple threads. And I don't think that's practical, although I've seen people talk about it, because you now have a locking issue related to trying to maintain the budget to make sure that the servers, you have 2 threads running at once on the same budget. Who's going to exhaust the budget first? An interesting, difficult to implement problem. Let's So locking, we had priority sealing, priority inheritance, all these things. They aren't very sufficient. They aren't sufficient for multiprocessor environment. This area I don't really think is very well understood. One thing is certain is that if you're going to use simple locks, you're going to have to be willing to wait sometimes, spin locks, wait for another processor. Once you get the spin lock, what you do is debatable. You know, one view is we should look at priorities, and then if the wrong guy is running, we give up the spin lock and pass it to somebody else. Another view is, well, you've got the spin lock already, your critical section better be short. Get in there and do it and get out again. The people working at University of North Carolina have very good experimental data that shows, at least in the Linux environment, it's better just to use the spin lock alone. When you've got the lock, use it and do FIFO queuing for the order of service for people that can't get locks. But one thing is definite, one size does not fit all on these locks. If you're talking about partition scheduling versus global scheduling, answers are different. You're talking about in partition scheduling, local locks versus global locks. You're talking about short critical sections versus long critical sections. Different answers for each one of them. Certain facts, the impact of the global locking on your execution is going to grow with a number of processors. Periodic execution will create natural synchronization, which maximizes contention. Parallel decomposition algorithms tend to create barriers which maximize contention. And so you actually end up getting, the actual algorithms tend to foster contention for locks. A weakness of global scheduling is you need global locks. And the other forms of scheduling don't have that problem. Okay, lock-free methods, I'll just mention them. There are a lot of good ideas there, including, which I didn't mention, transactional memory. It sort of extends the idea of read, copy, update. But they require you use specific solutions for specific problems. They aren't just locks. They don't replace locks one for one. Okay, so here we are. So we had this beautiful house, we've had a nice foundation, and then something happens. Okay, I really feel that the foundation in this case was built on a sinkhole. Okay, and it looked good. There's a big void underneath it. The assumption is that the actual workloads and processors fit the models, and they don't. One problem that seems to be ignored is data flow blocking. On a single processor, if you have a producer and a consumer, if one of them has to wait for the other, it means the processor is executing the other one. Okay, so that progress is being made. So there's no delay caused by that. No idle processor time. On a multiprocessor, if you have a producer and a consumer and they're on different processors, and one of them hasn't produced for the other one, the mating one waits. So if the consumer has nothing to consume, the producer is running, the consumer is just sitting there doing nothing. Okay, so we actually have kinds of blocking related to the logic of the tasks. We have to worry about data flow between tasks on the multiple processor. It becomes a big deal. Ignoring the architecture is just logic of the software. So the notion of independent tasks on which most all the analysis is based is just wrong. You know, and we can't limit it to critical sections of just holding a lock is short, we can narrow it down. We have maybe long sections where we're waiting for someone else to do something important that needs to be done before we can do our computation. And then there's the myth of worst case execution time. Even on a single processor, I've come to not believe in worst case execution times. If you have, well, cache is a problem, but people have tried to beat the cache problem to death by brute force trying to model cache behavior. I don't trust that because most of the papers I've seen on that subject, the only validation they have is against simulations. I haven't seen, maybe some of you haven't and can educate me on this, but I haven't seen people actually using it on actual hardware. Maybe that's past that level. But the next level, though, is DMA. As soon as you have a sizable I/O load and you have a bus that's accessing the memory, you have DMA competition, and you have no way to model that normally, okay? Except real worst case. Look at what's the maximum worst case load of the DMA. Suppose the memory is interleaved, it's 2 to 1 or 4 to 1, and the DMA gets a quarter of the share of, maybe you can do that. But That's bad enough.